just a little bit of a tour of, so if you recall last class, we have all of these things in DevSecOps that we could focus on. And I'm going to select two things out of this whole, this entire field. And, we cover some of this stuff in other courses, but it's just too much material for me to talk about in one class. So I'm going to talk today about language selection and why you shouldn't use C or C++ in any new project. And then on next week, next Tuesday, I'm going to talk about software component analysis and supply chain issues. So those are the two topics I've selected for application security. But I wanted you to see this because I want you to know that this is not an exhaustive treatment at all. It would be really cool to have a class that does all of that, but we just have bits and pieces scattered throughout our program. Okay, so I'm going to talk about programming languages and security. And the motivation for this is that a lot of security vulnerabilities are there, not just because we've misconfigured a network or misconfigured an operating system. They're there because we've written poor software. So as it turns out, we're introducing bugs much faster than we are removing them. And that's just the nature of software production. And so these three underlying issues are prevalent. We have the inability to build bug-free software. We have the trade-off when you get in there into industry. The trade-off is that your manager is going to want you to develop something fast and to deploy it. Speed is essential in something like a DevOps environment. But if you really want to do something securely, you have to do it by construction, and it takes longer. And I go back to this story between Multics versus Unix x86. Multics was was a project in which they were trying to do an integrated secure sort of operating system with a hardware platform that did hardware protection for security concerns, that did, a strongly typed programming language to ensure that, software errors were harder to code. And then what came along was Unix and x86 took all these shortcuts just to get to market fast. And because we have this, they won. The first to market wins. And this happens in the West, like when you're building a startup company, you have to get to market first in order to get all the user base. But then you take shortcuts, and those shortcuts can cause you security issues down the road. So this is a pattern that started, well, it probably started before Multics and Unix, but this is a pattern that repeats over and over again. And as a result, we have, and in fact, we'll talk about x86 and why 30 or 40 years after this, we're still trying to fix this problem of doing things incorrectly at the beginning and having to remediate all of these issues that have come along after. And then the last thing is secure software development is a work in progress. We don't do a lot of that in this curriculum, I have to admit, in the CS curriculum. We're still teaching C and C++, and we're still teaching it in a way that if we have our graduates go and program C and C++, they're going to program vulnerabilities straight off the bat, because it just happens that these languages are really hard to get right the first time around. So it all starts with their programming language selection. I would say this is the single biggest impediment to having secure applications, is your choice of the programming language. So the question that you might like, say you go out and you want to start a new project, the questions you want to answer when you choose your programming language is, if you're going to build something that's high performance, mission critical, what language would you want to choose? And so right now, if you don't have any experience in programming languages, you choose the one that you're familiar with, right? And so this is a problem because most of us in this curriculum, we're familiar with C and C++, so we choose C and C++. I'll try it in that language. But what happens if it had to be developed and delivered in a month using whatever your programmers know? And now this is going to be a hard sell for C and C++. Rapid development in C and C++, well, say I have to build a web server. How do I do that in C and C++? How do I take my 162 and 163 and those courses in our curriculum and build a full-fledged web server, web application in a month? So you're like, okay, probably should choose something else. So that's one of the things that you should keep in mind. What happens if it needs to be kept secure? and allow for continual updates. And again, your choice of programming language and whether or not it needs to be recompiled to deal with security updates is something to consider. Okay, so there is a fundamental tension when you are choosing programming languages between all of these concerns. So safety and security, performance, the ease of development and the development velocity that you can reach when you're developing in a particular language. You actually have to pay attention to the developer community, right? Like if you have a rich developer community that can help you out when you get stuck, that actually matters for your productivity. And then how is it that you maintain code after the fact? And how easy is it to maintain that code base? All of these things are considerations when you choose that language. And so initially, the language that we had at our disposal was C. And so in CS201, I call C a thin layer over assembly language, and it had its benefits 40 years ago. 40 and 50 years ago, in that compared to assembly language, it actually abstracts out a lot of the hardware details. So registers and memory addresses, and the ability to not have to manage those by hand in assembly was very convenient, right? You didn't have to manage variables, for example. And so C is giving you all of these abstractions that we rely upon. Things like variables, functions, data structures, such as arrays, and then all of the arithmetic and Boolean expressions to implement higher level functionality. Compared to other higher level languages that were developed after C, one of the things that people liked about C is that it compiles all the way down to machine instructions. And that's typically the fastest way to execute, is executing on what they call bare metal. Like the program goes straight into instructions that will run on bare metal. This is different than something like a Python or a JavaScript language where you have an interpreter that's implementing a simulated virtual machine, and then that interpreter runs on bare metal, but your program runs through an interpreter. So that's a little bit, I guess it's a little higher overhead, and it makes your program run slower. Okay. So C, because it was the best option out there, is now being used in a lot of essential applications that we rely upon, and especially those applications that require high performance. So all the operating systems are written in it, all the sort of the high performance web server, well, most of the high performance web servers. This is shifting actually to other languages as we'll see later. Web browsers are written in C and C++ mostly. Graphics card programming, so OpenCL and general purpose GPU programming, a lot of that stuff is written in C and C++. So what are some characteristics of C? Well, one of the first characteristics you'll note is that this precedes modern languages with these rich open source package repositories. And this is what makes C development painful when you want to build something complex, because you're not able to rely upon a whole bunch of other code that other people have written to leverage things like building a web application on top of. This is actually good and bad. It's good because then you don't have to rely on supply chain issues from developers you don't know anything about, right? But it's bad because it slows down your development time. The other characteristic is that because it's compiled to machine code, it's typically fast. You don't need a runtime to be shipped with your application. When you have JavaScript or Python, it turns out you have to actually ship with your Python script the Python interpreter, or with your JavaScript program, the JavaScript VM. And so, and then all the packages that you rely upon. With C, you could just compile that down to a binary, ship the binary, and it'll just run on any CPU. One of the issues with C and compiling to machine code is that you can't patch things in place. If you have a bug in one of your libraries, you have to recompile and relink. And so you can't, as an operations team, if you've deployed an app, an operations person can't just go and patch that buggy implementation. The operation team person has to go back to the developer and say, hey, recompile your buggy application and ship me a new version that doesn't have it. And so this is the problem where dev and ops have to basically be both involved to fix a security issue, which is a drawback. it's statically typed. And so one of the nice things with C is that if you are mixing and matching types that shouldn't be mixed and matched, the compiler catches that and tells you there's something wrong here. So a lot of bugs are caught at compile time when you have static types. And if you take any of our programming language courses in this department, static typing is a necessity if you want secure code and code that you can reason about. And so we're in our department, we have a lot of expertise with that. And the idea is that any mismatched type will get caught before you deploy that into a system. And then in contrast to dynamically typed systems such as Python or JavaScript, you don't need to have code in the interpreter to check the runtime types of things before executing the operation. It's all assumed to be matching when you have it statically typed at compile time. The one issue with C is that it is a weakly typed language. And so the difference between a weakly typed and a strongly typed language is that a weakly typed language, if you do have kind of mismatches in types that are allowable, what C will do is it'll do an implicit conversion of one type to another. And then you are allowed to explicitly cast a variable in one type to another type in your program. And there are strict rules for what happens when you do this, but sometimes this is being done under the covers and then the programmer doesn't have any idea this is happening. And I'll give you an example of this. This is called type coercion. The idea that the data type underneath can automatically change from one to another. So here's an example, a very simple C program. In main, I have a character, which is a single byte character of hex 80, and I just want to print that byte in hex. Now, I compile that and I run it, and you're like, oh, this thing should print 80, right? But instead, it prints this. So what the heck happened there? Turns out there is an implicit type conversion from a character integer to a 32-bit integer, an 8-bit character byte to a 32-bit integer. And that's being done with C underneath. And so this is an issue with weakly typed languages that allow this. And PHP is probably one of the worst ones for this, but we'll talk about that I talk about that in the web security class more. But here's another one that really boggles the mind. This only happens on x86 processors on Linux. You get different behavior if you're on an ARM for this, because a character byte on an ARM is unsigned. So you would actually get hex 80 on an ARM device. So we have a mixture of ARM and x86. So this is basically, this program is going to do two different things when compiled on two different platforms. So that's an issue with C. Okay, so I'm going to talk about more reasons to avoid C. Yeah.
Is that something that an interpreter litigates?
Yeah, so typically with an interpreter, you have one sort of blessed version of the VM that will interpret things in one way. With C, we have all sorts of different compilers. It turns out this is a compiler implementation thing where you're not sure. There is a spec, and the spec has things that must be done, and then some things that are recommended to be done. And then as you implement your compiler, you may or may not be fully up to spec. And this is the kind of stuff that happens when it's underspecified, and then one compiler chooses one way, the other compiler chooses another, and then you're stuck with the fact that you can't reason about this code anymore because it involves a compiler that you don't select until you're ready to build your system. And then as we saw earlier, when they change the compiler versions, like my labs break. This lab breaks, so I just have to fix that because when they ship a new compiler and the semantics of the compilation change, then the C code is unpredictable. Or my C code in that code lab is unpredictable, and so you have to be on your toes with this kind of stuff. Okay, so this class is about why we need to avoid C and what are the ramifications of using C that has occurred throughout the last 30 or 40 years of living with this language. The biggest thing for you to remember out of this class is that C allows unmanaged access to memory. So any program can get low-level direct access to memory locations in the process. This is good for speed. You can do a whole bunch of things more efficiently when you have direct access to memory that's not mediated by an interpreter, for example. But it's really difficult to write code when you're given this kind of access. And if any of you have taken the 162 and 163 sequence, this is really difficult as your very first language to learn. And so it's a testament for any of you who've gone through that sequence that you're still here, because this is enough to get people to say, like, CS is not for me. And this turns out to be the case in our program. People are like, whoa, there's way too much stuff here. What is this segmentation error? I thought I wrote a correct program, but I'm getting these random errors, like the compiler is not compiling it. When I run it, I get a seg fault. I have no idea what's going on. I have to learn how to use a debugger in order to figure out what the thing is. And so this is why it's like, okay, we should probably find a better way to teach programming. And that better way is something that's not C, but that's just my opinion. Well, it shouldn't. So yeah, that's another philosophical thing. I don't believe in the weed out up front by using like your ability to be resilient towards the issues with C, to love how to program and want to be able to build things. Because in the end, a functioning computer scientist doesn't need C in order to be functioning. And so like, we should be able to produce computer scientists without this obstacle right up front. But there's a whole bunch of people who could have been computer scientists who are like, I don't want any part of C and C++ and how this whole thing works, that we're turning away. But that's more my opinion versus what other people in this department might believe.
Programs written in C and C++, so those are still pretty common in the wild, right?
Legacy code. So yeah, if you plan on getting a job maintaining a browser or a web server or an operating system, you would do it in C. But there's so much more code out there. The percentage of people who actually do that kind of work is shrinking more and more as we go on. And replacements are now, like for new projects, you're not seeing a bunch of C and C++. So we offer a COBOL class here in our program. So if there is demand for COBOL programmers, but I can guarantee you're basically maintaining legacy code. And that's basically what C and C++ is going to be eventually. And you see I teach the cloud class, and a lot of that stuff is not written in C anymore. And this is where I think encouraging people not to rely on C and C++ as their main language is a benefit to all of you, since we're an CS program. Okay, so C allows you access to memory with no bounds checking, meaning you can access any address you want, and there is no runtime to say, hey, you shouldn't be doing this. There are no access control mechanisms that separate the areas that you're using for program instructions and the areas that you're using for data. Well, I mean, there's limited access control, I should say. Now there's more. Before there wasn't. And then there's no management for dynamically allocated memory. So when you want to allocate memory for a new data structure, you are forced to manually allocate that and manually deallocate that. And any bug that you have in that sequence causes a security issue. And so if you're not good at bookkeeping, like, yeah, I'm kind of a mess when like cleaning up after myself at home, at least. Don't expect me to be able to manage successfully cleaning up after myself in a programming language where I'm allocating memory and trying to deallocate that. It's just, I want to use the variable, but I don't really necessarily want to clean it up. You see that pattern a lot, and this is hard to get right. This leads to all of these confidentiality, integrity, and availability attacks as a result. And this has cost, over the last 40 years, tens of billions of dollars can be traced back to this particular issue. So Morris Worm, Code Red, NIMDA, SQL Slammer, Petya, not Petya. These are all the results of allowing programmers this unmanaged memory access. All of the browser bugs are like, I think it's like 3/4 of the browser bugs are because of this still. So yeah, this is a problem. And we have now invested hundreds of millions of dollars on remediation techniques. So we are trying to bake into the CPUs a bunch of countermeasures that really are programming language that derive from the fact that we have this programming language that is allowing this. And so we'll talk about these things later, these hardware mechanisms for fixing the problem of unmanaged memory access. So just some examples of this. So Heartbleed was a confidentiality attack, and this was because of a buffer overread in OpenSSL. So this is all the web servers are running OpenSSL, and this particular vulnerability allowed anyone to get the private key of any web server. And so if you think about, oh, all of our authentication over the web is because of these private keys that we're issuing in certificates for TLS certificates, this bug allowed anyone to read anyone else's private key, this Heartbleed bug, and this was in 2014.
Literally because of bounce check, lack of bounce check.
Yeah, and I'll show you. So this is XKCD has the best explanation of this. So the Heartbleed bug says, oh, are you still there? This is a heartbeat message, and say, if you're still there, reply to potato with 6 letters. And then you see over here, potato, 6 letters, and the server's like, oh, I'll send you potato, 6 letters, no problem. And then the next heartbeat message says, oh, if you're still there, reply with bird, 4 letters. And you say, okay, I'll send you bird with 4 letters. And then the adversary is like, oh, reply, if you're still there, send me hat with 500 letters. And this thing will just read 500 letters, even though hat is 3. And then you can see somewhere in there, hey, here's my server master key for TLS in italics here. That's basically the bug. And these are the lines of code where you're basically parsing the length from the heartbeat message, and then you're using it to do this memory copy on the response. And so that's basically the issue. There's no input validation, and then nothing checks the overrun. So this is basically it right here. The payload length is never checked, and then this mem copy happily just takes whatever the user input asked for in terms of the length, copies out that entire buffer back into the response. So that's the bug. And this is because, well, this is C, I think it's in C. This is basically written in C, and there's nothing to protect against this behavior. We have integrity attacks. So this is just from earlier this month. This is a buffer overflow that may, quote unquote, may lead to remote code execution. So you overflow a buffer and you inject stuff that actually gets the CPU to execute your code rather than the SSL code. So that's an integrity attack because that server is no longer running what it's intended to run. It's running what you have injected into that. So, and so one of the things that if you look at the fine notes of this, you're like, so this could potentially lead to remote code execution, but there are modern platforms that implement Stack Overflow protections. We'll get to that at the very end. All of these mitigations that we've had to put in place to prevent just this thing is what's the only thing that's stopping remote code execution. So we'll talk about that hopefully at the end of this class or maybe next week. Okay, and then we have availability attacks as a result of this vulnerability. So this was the original ping of death vulnerability from 1997. So the way this worked is you could send a single packet to a server and cause it to crash. So you can just take down servers because of a buffer overflow. And this was the ping of death packet. You send this enormous ICMP packet that's over 65,000 bytes. And then the attacker sends that to the target. And because it's such a huge packet, it'll get fragmented. And so IP doesn't like, IP and most data link layers don't like packets this size. And so it'll get fragmented. And then the target system has to reconstruct the original IP packet with the fragments. And because it doesn't think that it's going to get an enormous packet like this, it just causes a kernel panic and then crashes. And so this is basically a buffer overflow that crashes the target system. And so this is a long time ago, but as it turns out, there was a long-awaited sequel in 2020. And so I went back and looked at the time frame. I don't know, have any of you seen Top Gun Maverick? You know, that was basically that sequel was at least 25 years after the original. So this is close. This is a little less. So this basically happened where you send a single packet, and this is a DNS packet. So you run this script that sends a DNS packet to this IP address as an IPv6 IP address. And then this is the machine that's running. And then you can cause this thing, because of a buffer overflow, you can cause this entire machine to crash. So that's an availability attack. What's hilarious is that even adversaries have this problem. They're writing their malicious code in C, and then analysts are like, oh, there's a buffer overflow attack in this Mirai code. And this was in 2016. We've covered Mirai before. It's like you could send Mirai a request that causes it to crash. And that's what they did. And so they were like, oh, just overflow a buffer and then crash the Mirai process. So yeah, Mirai's adversaries might want to consider switching over from C to something like Go. And actually they are. So the incidents of the occurrences of Go-based malware, and I don't think there's a lot of Rust-based malware, but definitely a lot of malware is being written in Go now, which is a thing. And this motivates, a couple months ago, the Microsoft Azure CTO saying, you know what, we should stop using C and C++ for new projects. Consider these languages deprecated. And NSA sends the same message to developers. You know what, shift over to memory safe languages. And so this class is all about giving you reasons why to believe that advice. And so we're going to talk about all the different kinds of memory errors. Well, we're not going to, not all of them, but we're going to talk about one in particular. But there are a lot of different memory errors that we could cover. But the easiest one for me to explain and to show mitigations for will be the buffer overflow attacks. And this will be a little bit of a review if you've taken CS201, but for those of you who haven't, this will just give you an idea of the issues that memory corruption can have on the execution of your program. So there's buffer overflow, and then there are heap vulnerabilities. So the heap is where we dynamically allocate memory at runtime, and then we deallocate from the heap structures when we're done with that memory. And so that's another set of vulnerabilities that we'll talk less about in this class. So I'm going to talk about stack smashing, which is the original, a common buffer overflow attack. It was one of the most prevalently occurring remote security exploits in the early 2000s. But the thing is, this is still around. So here is a buffer overflow attack on sudo, which allowed instant privilege escalation for anyone who had it. And so like this binary, like if you have a version of Linux that is across these 9 years, it has this vulnerability. So you can, if you find a system that hasn't been updated, you can basically leverage this sudo vulnerability to get root on that box. And so we talked about privilege escalation in the last class. This is one of those things where if you have this database of what are the exploits for this machine, you can just basically pull this out and get root on your system. And so here's an example of it being exploited, where you just say, so in Perl, you can just say, give me A 100 times, and then null 50 times. And then you pass this into sudo, and it basically causes a seg fault. And so seg faults are an indicator that you corrupted memory. And then adversaries are really good at, exploit developers are really good at taking a memory corruption bug and chaining it to get full code execution. Usually this is your telltale sign that you can actually get code execution on this thing. But the details are, again, something I'm going to skip. So to understand the stack smashing attack, I'm going to do just a brief overview of the things that we talk about in CS201. The first thing I want to talk about is the x86 architecture. So on a CPU, you typically have this program counter, and on x86 it's called the EIP. And this is the pointer to the next instruction that you're going to execute in memory. You also have in the CPU a bunch of registers, register state for heavily used program data, and then condition codes for implementing conditionals and branches in your processor. And then all of this interacts with memory. And so in memory, and because we have a von Neumann architecture versus a Harvard architecture, we have one big bank of memory where program code, program data, operating system code, and operating system data, they all reside in one shared memory. In a Harvard architecture, the instructions are separate from the data. But in a von Neumann architecture, which most of our architectures are, they're conjoined. And this is a big problem, actually, because then you can mix code and data and then be able to execute data that should be treated as data which is an underlying vulnerability. Okay, so the memory is basically a byte addressable array. This is a flat array of memory, and it holds all of this data and code. It also includes an area of this memory allocated for the stack, and the stack is used to support function call invocations. And so when you think about calling functions in a chain, it's a last in, first out kind of operation when you do function calls. Last in, first return, or last call, first returned is the idea. Okay, so the way we implement function calls on the stack, I'm going to show you an animation. So this is a program. It's a very simple program. It calls so the main program calls a function. The function has a variable, and then it will eventually, after it's been called, return to the location in memory where it was called from. And so this is this calling, the function calls are implemented on the stack. And so this is a picture of what the stack looks like as we are doing these operations. And so on x86, the stack starts at high addresses on the top. And as you push things onto the stack, you basically go towards decreasing addresses. So the lower addresses are on the bottom, higher addresses are at the top, and the stack pointer register is pointing to the top element of the stack. And as you push elements onto the stack, you're going to decrement this stack pointer. Okay, so what happens? So we're going to do this call. We're in main, and in main, we call this function. And when you call the function, you want to actually save the return address from where you're at onto the stack somewhere so that you can, after the function is done, you can return back to this. So this is what happens. So when you do a call function, the return address in main is pushed onto the stack. And then you're going to invoke this function. And as part of this function, one of the things that you'll do is you'll save this old frame pointer. So your frame of reference gives you, well, which context am I in? Am I in the main context or am I in the function context? And so this base pointer is pointing to main's context. And so you save that, and then you update the frame pointer register, which is EBP, to point to the new context, which is this function's context. So that's what this value is pointing to. And so now the stack pointer and the frame pointer are pointing here. And then what you need to do is you need to allocate memory for this variable. And so then what you'll do is you'll update the stack pointer to point beyond this integer x that you've allocated. And then in this case, this is actually, well, on a 32-bit machine, this is actually 4 bytes, not 8 bytes, sorry. So that's basically a picture of how functions get called and the values that you push onto the stack. Okay, so here's a simple program and how it should work. So you have this function, say you call into it, you have the return address, the base pointer, you have this integer x, and let's say you've allocated a character buffer that's 8 bytes. And so you have buffer 7, buffer 4, buffer 3, buffer 0, and these are the 8 bytes of this buffer, little b buffer. And then what you do is you say, I want to do a mem copy into this buffer, the string A, B, C, D, E, F, G. So this is 7 bytes. And then the last byte will be a null terminator. And so I'm going to say for those 8 bytes, it should have A, B, C, D, E, F, G followed by a null. And then I'm going to just print the contents of that buffer and then the integer x. And this is what you should have after execution of this function, right? You've copied A, B, C, D, E, F, G with that null. And then this, because you initialize this integer to 0, this stays, this is all cleared. So this is how it should work, right? But if you have programmed a bug and you have programmed an overrun where the amount that you're copying into this buffer is bigger than the buffer contents itself, when you execute something, when you execute this version of the function, you're going to get something that looks like this. And so what you'll do is you'll go do A, B, C, D, E, F, G, and then H. And then this is the ASCII for I, the ASCII for J, and the ASCII for K. You'll completely overrun this buffer and corrupt this integer x. So this is the classic buffer overflow. And then when you print this integer, you get this value interpreted as a decimal. So this is how you get that garbage. Okay, does this make sense for people?
Yep.
Okay. So the buffer overflow attack is to trick the program into overwriting memory it shouldn't. And so again, you have these buffers and you want to overrun this. And the thing that's up here that you might want to overrun to get code execution is sitting right here, this return address, because then you're able to hijack execution. Okay, so that's the idea. So this return statement in C, if you have done this copy and you hit this return, and this copy has corrupted the return address, you can place a different return address onto the stack and then force this program to jump to that new address after you've done this memory copy. Okay, so that's the classic one. And so the idea is that maybe you will inject some malicious code into this buffer. And then what you'll do is you'll craft a return address that will return back into this malicious code. So that's the classic buffer over the Stack Overflow vulnerability. Okay, so I'm going to give you a new picture here. This is your vulnerable buffer, and then this is your return address, and we're going to be writing into this buffer from left to right. And so the idea is to get your malicious code into this buffer, and then eventually on the overrun, emit an address that will return to the location of wherever this malicious code resides. So that's the ideal look for this. But we have a problem here. You can't just go and like, we have some missing things here. You can't just calculate an address. You know, we don't know exactly what this should be ahead of time. And so you need to figure out where this where this buffer is located in memory in order for you to write the address that returns to it. So that's one of the things that we have to solve. And so, well, there's two things. So one of the things is finding this address, and then the other thing is being able to figure out where to set this address as an offset from the injection point, because you don't know how much stuff is in between the beginning of this buffer and this return address over here. So those are the two things that we're going to talk about. The first one is not knowing the offset between the injection point and where this return address is located. And one way to solve this is to just spam this return address everywhere in memory, and then eventually you'll hit this return address that will return you back to the malicious code. So that's one of the issues. The other problem that I talked about was that you don't actually know the address of the injection point ahead of time. And these addresses are absolute and not relative. You actually need to give me a virtual memory address here to return to. And so one of the ways you can find the insertion address is that if you have a copy of the vulnerable binary, and you would in an open source, if you have an open source server that's vulnerable, you could basically run this, load it up into a debugger, and find that address. Where does that buffer start in memory? And so this is an example. I have to figure out where this buffer is located in memory in order for me to overrun main so that the return address returns to the beginning of where this buffer is. And so you could basically inspect the binaries that get shipped to figure out the memory address of this buffer. And here's an example of loading this binary up into a debugger, figuring out what the stack pointer points to when you enter main, and then taking a look at the address of this buffer, and then you'll realize I need to return into this particular location, is the idea. Okay, what happens if you get this wrong? So one of the issues is that you must set the instruction pointer on that return correctly, otherwise you'll end up with garbage instructions in memory. So unless you set it exactly at the beginning of your malicious code, you might get bogus instructions that are executing and cause that remote server to crash instead of doing your exploit. And so one way around this is to do something that's called a NOP sled. What I'm going to do is I'm going to inject a whole bunch of no-ops, which are single byte instructions that don't do anything. They just increment the instruction pointer. And then anywhere in this NOP sled, is fine for you to return to, because then it'll just run through the NOP sled and then get to your malicious code. And so this is a technique to get reliable code execution from a remote location. So yeah.
I'm sorry, so the malicious code again is injected by just where there's input, just overflowing it so that it grows up. the
Yeah.
stack, and then and overwrites like program code previously.
Yeah.
Like,
Stack data. Yeah.
stack data.
Yeah. So here's an example. You have a vulnerable buffer and you're reading input into this buffer from the adversary, and it's done in a way that's unbounded. And so if the adversary gives more than 500 bytes, then this is where the adversary can inject the shellcode, overwrite the return address, and have that thing returned to the beginning of this buffer. Yeah, that's the general pattern of the vulnerability. And so this is the anatomy of a real buffer overflow attack. And this is something that you'll do parts of this in your lab by constructing, by overflowing this buffer, figuring out where the return address is and returning this address over to some location in this buffer. It might be preceded with a NOP sled, and then you'll execute your malicious code. And that's the typical, this is the base pattern for this buffer overflow attack. Okay. So I showed you some malicious code to execute, but what is that code? What is the code you want to execute? Well, how do you access a machine remotely? Well, you typically access a machine using SSH to get an interactive shell. And so the malicious code that you want to execute typically involves getting a shell on that machine, and then you can do arbitrary things to that machine. And this is what you'll be doing in your labs, actually. You'll be trying to invoke an interactive shell. Okay. Is that enough? Well, code execution is one thing. One of the things that you would like to do is get code execution as the root account. And so you might also want to do a privilege escalation on in your malicious code, and then and then invoke a shell. So there are some shell code sort of programs that attempt to elevate privileges and then execute the shell. But for the most part in this class, we're just going to invoke the shell. Okay. Okay, so typically when you're injecting shell code, you're going to try and find a vulnerable set UID program that's got this buffer overflow in it, and then force it to set its real UID to 0, and then execute bin shell is the anatomy of this attack. Okay, so in C, spawning a root shell is 2 calls. There's a set UID call to set UID to root, and then an execve, which is to invoke a program to replace the operating program with a new program, which is bin shell. And this is, again, straight from 201 and 333. And execve has 2 arguments, or three parameters. It's got the command you want to execute, and then the arguments to that command, and then the environment you want to pass to it. For simplicity, an adversary doesn't care about the arguments. It just wants the interactive shell, and then the environment it doesn't care about either. So these 2 things are typically set to null in an exploit. You don't care about those. So if I set those parameters to 0 and I invoke the execve system call with a pointer to a string that says bin shell, I'll get a shell on the other side. Okay. So here is some assembly code for doing just that. And this is the assembly code that was in the other slide. And I don't really want you to pay too much attention to the shell code, but there's a library of all the different shell codes on every single CPU platform. I think it's in shellcode.com. You can look it up, or shellstorm is the command. So this is just one example pulled out of shellstorm. And there's like I think it's a 24-byte payload. So this is all you need. Inject these 24 bytes, return to it, and then you get a shell. And so this is what it's doing. It's zeroing out a register, EAX, and then it's pushing this a null followed by an ASCII string that represents bin shell onto the stack. Because again, you need to invoke execve with a pointer that points to this string. And then what you're going to do is you're going to move the current stack pointer into a register, because now you want this register to point to bin shell as part of your system call invocation. So that's what the next instruction does. And then you're going to null out the other two registers used in the execve call. So you're basically trying to call execve bin shell 00. The parameters are stored in EBX, ECX, and EDX for this system call. And so now you have a pointer to this string, you have two nulls, and now you can say, I want to invoke execve, which is system call number 11. So I'm going to put the integer 11 into, this is the low word of EAX. And then I'm going to do an int hex 80, which is the system call interrupt. And so this will invoke a shell and spawn a shell on that victim process. Okay. So now this is what we have. We have a NOP sled, we have our shell code, and now we can spam this new address. And now we can point this to any vulnerable program and then get code execution onto it. Okay, so here's a picture of it in practice. So here's my function. My vulnerable buffer has an unbounded strcpy from a string up here that I pass it. So I pass this function some large string. And in this case, the large string is 256 bytes of the capital A. So that's what I'm doing with this program. This is a picture of the stack. And again, we're going from left to right. The first thing that happens when I call this function is I have to put the pointer to this string onto the stack as a function argument to this function. So that's what these 4 bytes are. And then I'm going to call the function. And when I call the function, I have the saved return pointer for where I'm going to return to on main. And that's basically what this is. And then when I get into the function, I have the frame pointer allocated so that I update the frame pointer from pointing to mains frame to pointing to functions frame. And then what I have is that buffer. So I have 16 bytes allocated onto the stack. And this is where I'm going to do the strcpy from this pointer that has this. So this points to this large string of A's. And I'm going to copy that large string of A's into this buffer. But this is an unbounded strcpy here. And so this is what's going to happen next. I am going to, So I'm going to put these two parameters. So before I call strcpy, I'm going to put the pointer to the buffer and the pointer to the string as arguments onto the stack before I call this strcpy. And then what the strcpy is going to do is it's going to actually perform this copy between the input string and this buffer. Okay, so this is what happens. So I have 256 capital A's, and it goes well beyond this picture, right? And so now I've corrupted a whole bunch of stuff onto the stack. And when the strcpy returns, when the function returns, you can see this function, the return address has now been corrupted to be something other than what it was to begin with. So then the next part of this is when I return from this function, I'm going to restore the frame pointer, and the frame pointer is going to point to garbage. So now the frame pointer has basically capital A. The hex representation of ASCII capital A is hex 41. And then my frame pointer is basically going to point to hex 41, 41, 41, 41, which is all the capital A's. And then when I try and do the return also is pointing to hex 41, 41, 41, 41. Now, when you try and return to this instruction pointer, what do you think is going to happen? Something positive? Yeah, this is going to give you a seg fault because this thing doesn't point to any memory that you've probably allocated, unless you've intentionally put something at hex 41, 41, 41, 41, but it's unlikely, right? So in our buffer overflow attack, we would, instead of doing hex 41, 41, 41, 41, we would actually want to overwrite this with the address of buffer. And then instead of all capital A's, we would want to put shellcode in there. This is just an animation for what is going on underneath. Okay, so your Narnia level in the lab is going to have you practice this. So here is the program that you're going to exploit. And the idea is that you have a 20-byte buffer here, and then you have a value that basically this scanf is a 24-byte scanf that points to this buffer. And as it turns out, because there's 4 extra bytes here, this scanf, if you give it 24 bytes, will overwrite this value. And then what this program does is if the value is equal to dead beef, then you get a shell. This is like your original, the easiest buffer overflow program that you could come up with. And then you invoke this base system is a library call that basically does an exec VE of bin shell with null and null. So you're basically doing a system call with this library call. And then if you don't set that thing, it says you're way off, and it will actually print this value. So this is helpful. It'll print your value just so you know which bytes you're overwriting. And so there's a walkthrough, the very first walkthrough in the lab, which is fixed now, will have you do this. Corrupt it in a way to get you dead beef as a first step for the memory corruption error. Okay, are there any questions about buffer overflow attacks? So in my version of CS201, I do cover this, but just in case you haven't seen this before, this is what the labs are about when it comes to application security. Okay. The next thing I want to talk about is return-oriented programming. So what is this? Well, one of the things they realized initially was that, you know what, we should never allow executable code to be injected on the stack. We should just say, you know what, anything in the stack, just don't execute that. And that's what this data execution prevention mechanism, which we'll cover later, does. So they deployed this. Well, this countermeasure was proposed, and they're like, yeah, this gets rid of the shellcode injection. But then some really clever researchers were like, well, I don't need to inject code of my own. I can actually use code that's actually resident in the process to invoke a shell. So stuff that's already loaded in legitimate code is going to be used to get access, to get remote code execution. So how is this going to be done? So the original approach was this idea of this return to libc attack. So the idea is to overwrite the saved instruction pointer with an address that returns to somewhere in legitimate code. And in this case, it's in the libc library code. And if you look at the library code for libc, it's often the case that the library call for system is there, right? This exact call that we're using here to invoke a shell, that's actually loaded into the memory space of every program that loads libc. And so then the idea is, hey, maybe I don't need to inject shellcode. All I need to do is corrupt the stack and have it return to this symbol system. And then what I need to do is craft onto the stack a pointer to bin shell when I return to this function call. And that's basically what the return to libc vulnerability or attack is. And so let's go through an example. Suppose this victim has the libc function system somewhere in its program, and it's resident in its code memory. And so the system library call runs an arbitrary program and then waits for it to finish. And so what we need to do is overflow the stack and get it to return to the address of system with a parameter pointing onto the stack that points to bin shell as the parameter to run system with. And that's what we're looking to do. The idea is to find that address in the C library within the target process, inject a command string into program memory onto the stack. And so this is data. You're injecting this string again onto the stack, but it's data. You're not actually injecting code. You're saying, I'm going to put bin shell onto the stack and then get a pointer to its address. And this is very similar to what you saw in the shellcode injection thing, where we're trying to get a pointer to that string. and then use stack smashing to clobber the return address, have it return to system with this parameter bin shell on the stack as its argument. And then you can execute this shell without writing shell code, without putting an instruction on the stack that gets executed. Okay, so this is what it looks like. Again, you have this vulnerable buffer, and you have a return address over here, and then here's some extra memory locations for you to play with because you have an overflow that goes beyond this. So in the buffer, you can start your overflow. So you start with capital A's. And then for the return address, when you get to this return address, what you're going to do is you're going to find the address of system in libc as it's loaded into the memory of the vulnerable process. So in this case, this is just regular library code. And this call is expecting a character pointer on the stack that points to the command that it's supposed to execute. Now, that needs to be stored somewhere onto the stack. And when you return to system, the stack pointer is here, and your arguments to system that point to bin shell have to be pointed to in this next part. And so you need to construct a fake calling frame for system, because if you're going to return to this, the program is going to expect a stack frame that indicates that you're in this function call rather than the original one that started this all off. And so that's basically what you're doing on this side of the overflow, is reconstructing that stack frame that you want. And one of the things that you want in the stack frame is, suppose you want to return from this system to somewhere else. This is when you issue a call, you're pushing the return address onto the stack. So that's the first thing you put onto the stack. The next thing you put is the address of the parameter. You're putting the parameters onto the stack before you issue the call. And so what you need here is the address to the string bin shell, because that's what you want system to use as a parameter. And so these are the things that you saw when you're calling functions in C. You're pushing the arguments onto the stack. You're issuing the call that pushes the return address onto the stack. You're just recreating that frame for this process to do it. And then you can inject the string itself, and then you just get this address to point to the actual string in memory. And so that's the anatomy of a return to libc attack in this case. So I'm going to have you do a level in this ROP Emporium CTF. It is like, I think I have you do the first 2 levels of this just to give you a flavor for what return-oriented programming does. And so you'll visit this site, ret2win. And then in ret2win, you'll see that this thing is not callable from anywhere in the binary. And the idea is that you want to overflow a buffer in a vulnerable function in order to get it to return to ret2win. And you can see ret2win has this address in it, 0804862C. So that's basically what you're going to try and overflow the return address for. And so they give you this ownMe function. And in this ownMe function, there is a vulnerable read that will read into a 32-byte buffer. So that's basically, this is a local variable allocated onto the stack. That's 32 bytes. And then it basically allows you to read in 56 bytes into this 32-byte buffer. And so this will allow you to overwrite the return address to ownMe to inject hex 0804862C. And so the code lab is going to show you how to exploit this thing in a sort of an incremental fashion. So this is an example of what you're going to do. You're going to say, you know what, I'm going to overflow this buffer. I'm going to put 44 bytes of capital A. And then at the very end, I'm going to put the return address. It's a little endian exploit. I'm going to put that return address to ret2win onto the stack. And this is what I'm going to send to the ret2win binary. And then you'll get basically a flag as a result of doing this. Okay, so that is return to libc. Return-oriented programming is a generalization of return to libc. And this is something that is really advanced. The idea is to inject a specially sequenced series of fake stack frames pointing to the end, the tail end of a whole bunch of functions. So in the process memory space, there's a whole bunch of code and there are a whole bunch of functions. And the idea is that you have this mechanism to return to any point in that code, but that code will eventually terminate in a ret. And so the idea here is if I inject into this stack a whole bunch of return addresses and I chain together a whole bunch of tail ends of function calls, I can basically build a Turing complete machine. And these tail ends of the function calls are called gadgets. And so if you have enough gadgets in your program, you can build a fully functional Turing complete machine. So you can get arbitrary code execution just using these gadgets. You might need to use thousands of them, but yeah, you should be able to get basically a fully functioning code that does exactly what you want it to do. And so the idea is to inject a whole bunch of stack frames, and then you return to that initial one. And this initial return will result in the first gadget being executed. And at the end of that first gadget, there's a return, and then that'll return to the next gadget in the stack. So you're basically popping off a whole bunch of gadgets until you get the thing that you want executed to run. Okay, so there are things called gadget compilers that will, based on the memory image of your executing code, will figure out what every single gadget in memory can do, like all the different abstractions that it provides. And then based on how the code you want to execute, it will compile the gadgets you need to generate an exploit. And so there's in the hidden slides, there's an example of doing this using a package called Anger. And this Anger ROP thing is basically a gadget compiler for you. Okay, so this is what it looks like. The stack pointer is going to basically be pointing to a whole bunch of gadgets, and these gadgets are all pointing to return snippets. So a set of instructions followed by a return, and when this thing returns, it'll go to the next one, and then it'll be somewhere else in your program memory, and typically this is in the C library, followed by a return, and this is how you're executing your code. And it's almost like each one of these gadgets is a single instruction in your computer. Okay, so this is the workflow of ROP. You find all the gadgets in the operating system and in the libraries that you can call. You can do a compilation sequence based on what you want to implement in your payload. And so Radar 2, Anger, all of these tools have automated ways of compiling gadgets. And then you inject data to write all of the gadget addresses into the stack. And this is what it looks like. So you have the first gadget here, then the next gadget, and then the next gadget. And this just keeps on going for as many gadgets as you're going to need. And none of this requires that you inject any code onto the stack. So the fact that you made the stack no execute doesn't matter. You're executing code in legitimate software or legitimate assembly code of your program. Okay, and then the initial overflow will inject all of this stuff in there and then cause you to return to the initial gadget is the idea. Okay, so note that no code injection is required, but this relies on a predictable memory address for all of those gadgets, right? You have to know where those gadgets are located ahead of time in order for you to construct a gadget chain that you can exploit. And this will become important when we talk about countermeasures to this, because if you change any of those addresses, this doesn't work. So that will be what we'll cover after the break. Okay, so I'm going to talk about the history of countermeasures. And really, you could have an entire course devoted to this. Like, there have been so many systems and proposals for addressing memory corruption errors. And so I've taken kind of a greatest hits approach to what I show you. And what I think is a greatest hit is it actually is being used. If it's a technique that's in a system being used to prevent these kinds of attacks, I'm going to show it to you. But just know that there's been a whole bunch of creative work around this space. And I only have whatever time is left in this class to show you what's out there. The first thing is language selection. And so the idea of what Microsoft and the NSA is saying is that, you know what? Stop using languages that aren't memory safe. We now have system programming languages that compile all the way to bare metal that are memory safe. Please use them. Before, like 20 years ago, we didn't have Rust. We didn't have Go. We had no ability to get a super fast binary that was memory safe. All we had was C and C++. We do not have that excuse anymore. So we have Rust to ensure memory safety and to ensure memory safety without the use of a garbage collector. So a garbage collector will wake up periodically and get rid of memory that's not being used. And some people don't like this. Some people are like, you know what, the compiler should be smart enough to know when you're trying to use memory and not deallocate it. And so Rust takes an approach where we're going to force the programmer to deal with the memory allocation. Whereas Go does have a garbage collector. So Go will wake up and monitor the reference count of memory and then clean up memory that doesn't have a reference count. Both of these will check out of bounds memory accesses and will error out whenever these things happen. So we should just use these languages. Performance-wise, they are within percentages of highly optimized C and C++ code. So this is the first thing. And if this is the only thing you get out of this lecture, I'm happy. you look at something else. The other thing you could do is say, you know what, I am going to try and save C and C++ programmers by if I teach them how to use the language securely. Now, if you have this approach, good luck to you. You're going to be doing a lot of teaching to a lot of people because this is hard to do. So you have to get rid of deprecated calls like strcpy. So using str and copy instead of str. I don't know how that slide came about, but that slide is just here. Let me fix that. Use bounded copies instead of unbounded copies. Use scanfs with length delimiters that are accurate. So we saw one that was not accurate before. So the idea is to use the ones that are accurate. And then using printf without format. So removing vulnerable formatted IO calls. And we didn't talk about format string vulnerabilities in this class, but that's another class of errors that C allows you to write. Another popular countermeasure, and this was actually developed here in Oregon at a place called OGI in the 90s, is stack canaries. So the project was called StackGuard. And the idea here is that the compiler is going to insert a canary, some kind of random integer, onto the stack when you enter a function. So it places this canary on the stack, and then it will check to see the canary is still there on the return. And if you have a buffer overflow attack that happens to overwrite that canary, the code will see that the canary has been corrupted and automatically terminate. So that's the idea. So we have this here. We call into the function, and then this is the return address. And then we push a random canary before we save the frame pointer and then execute our function. And if there's a buffer overflow in a buffer in our function that overwrites the canary in order to get at the return address, then at the end of the function, we'll check to see if the canary is still living. And only if this canary is exactly what it should be, will I return to that call. Okay. So it basically, this is what it looks like. So without a canary, so if you compile your program with no stack protector, there's a flag that says F no stack protector, you'll get this. It's basically, and this is the thing we teach in CS201. Push the frame, save the old frame pointer, update the current frame pointer, do the function code that you were going to do before, and then at the end of this function return. And so when you, by default now, when you compile a program binary, it's going to do something that looks like this. I'm going to push a random number onto the stack, And then I'm going to save the frame pointer. And then at the very end of the function, when I'm ready to exit, I'm going to compare the contents of the stack to that random number again. And it's only if they are equal that I then return. Otherwise, this canary changed, and there's a stack fail check call that will exit the program. So again, memory corruption that tries to overwrite that return address gets detected, the program stops. This should be on by default. I have to try hard to remove it now in order to show you what this mechanism actually is doing. And I think that's part of your lab when you compile some of these binaries. Now note, you can, if you know what this value is, if this value is actually statically compiled into this function, you don't want it to be statically compiled, just a hint. But say you implemented a canary, which is that says, hey, 34333231, this is basically the ASCII string 1234. If you know that this is the canary, then you could replicate the canary and then overwrite the return address. So it's important that the canary is not known by the adversary. Otherwise, the adversary might be able to inject the canary and then do the overflow, inject the canary, recreate the canary, and then overwrite the return address. Okay, to prevent that from happening, they were like, okay, well, you know what? We'll put a canary on the stack with a terminator guard. And the idea is that the value in the canary is such that it will terminate any stir copy. Any vulnerable string operation will terminate when you try and overwrite this canary, these canary bytes. So here is an example with terminator guard. And so I'm going to push this well-known pattern. So the null character, the line feed character, a non-printable character, so you can't put a regular string in, because ASCII is a 7-bit format. So you put something that has 8 bits in it, and then a stir copy can't generate this string at all. And then a carriage return. So if I do this and I have a vulnerable stir copy, there's no way I can overwrite. I can recreate this canary and then overwrite the return value on the stack. So that's the idea of stack canary with terminator guards. Another countermeasure is what I mentioned earlier, data execution prevention, or this no execute bit that is being added to the memory pages. And the first thing I need to talk about in terms of how this gets implemented is how memory management is done in between the CPU and operating system. And so this is kind of a review of your OS class, but the idea is that you have a memory controller embedded in the CPU, and it's managing addresses in process address space, and it's mapping them into the real memory that goes underneath. And so this is what it looks like. You have multiple programs running on your machine. Each one has this virtual memory abstraction where it believes it owns all of the memory on the system. And then what happens is that the memory controller and the CPU are going to map this program memory into the real memory underneath on the right. So in order to do this, they need to do this on a granularity that's large, because you don't want to have to do this on individual memory addresses. You want to do this in blocks of memory that you can bring all at once in from memory and out of. And so there is this idea of doing this in memory pages, and the memory page size is typically 4 kilobytes. So pages, 4 kilobyte pages are the pages that are brought into and out of real memory into a process virtual address space. So here's an example of paged memory. So you break up the memory address space into chunks of 4 kilobytes. So hex 1000 is basically 4096, which is 4K pages. And then what you'll do is you'll have a page number, which is the first part of the address, followed by the offset, which is the last part, these 3 values here for the second part of the offset in that page. And this is how paging is done in an operating system. You have all these discrete pages, and then addresses are just offsets into the pages. Now, the protection boundaries are being done at the page level. So when we specify permissions, we're going to specify them and attach them to the pages themselves, not to the bytes. And that's how memory protection will be done here. Okay, so then this is what happens. Say I have in my program memory, in program 1, I have a virtual memory address that says virtual page 0, and then an offset of 4 bytes into that virtual page 0 is where this pointer is stored. And so this is in virtual memory, but in physical memory, this might map to a physical page that's not page 0 in physical memory. And so in order to do this mapping, we have these page table structures in order to do the translation. So the translation from virtual memory for a particular process into real memory is what page tables are for. So it's going to map your PID and your virtual memory page together, and it's going to point you to the physical page in memory that you're needing to go to. And so in this case, here is the page table. I have a virtual page number for this process that is page number 0. And then I have an entry in this table that says, well, the real page is page number 3 in real memory. And then you can go over here and then realize that this is where this pointer is stored at. Okay, so this is what it looks like. So for the next address, I have a virtual address here in my program that's virtual page 1. And then in this in the page table entry, it says, oh, this is page number hex 302 in physical memory. And then when it goes and accesses that data, it's at page 302 in physical memory with that offset of 234. So initially, we have this paging architecture in x86. Initially, we have these permission bits, some bookkeeping bits that talk about whether or not the page has been modified, whether or not it's valid, meaning that it's the entry in the page table is a valid entry, whether or not it's privileged, which means that if it's a kernel process, then it's access to a privileged page, and then whether or not we have write access to this page. And these were all bits that you stored as part of your page table, and this controlled the properties of that page, the permissions onto that page. And so what the no execute and the data execution prevention mechanism is to add another bit. And the bit says, can I execute code from this page? So is this a page that has code that I am allowed to execute, or should it not be executable? Should it be no execute? And that's basically what this idea is. And for the stack locations and for the heap locations, the pages that back the stack and the heap, you probably want to make those no execute, right? And so that restricts shellcode from being injected into either one of those memory areas and then actually being executed if you have this turned on for your process. So that's the no execute data execution prevention thing. And so the idea is that do not allow a page to be both writable and executable, because code injection requires both. It requires you to write over a page with injected code and then to return to it to execute that code. And so all throughout the memory process, you should not allow a page that can do both. Okay, so no self-modifying binaries. Like that used to be a thing where you have self-modifying code. You used to be able to do that, but now we're telling you, please don't do that. In fact, we're going to ask you to turn this bit on and then have the operating system make sure, and the operating system and the CPU make sure you can't do this. And that's what data execution prevention is.
What's stopping an adversary from changing that bit?
The adversary has to get access first in order to change that bit. And so, yeah, if the adversary has a way of changing that bit without injecting code, then they can inject code.
So if data execution prevention was off,
Yeah.
and then they could switch it to be on, which doesn't do that.
Yeah.
But not the other way.
Yeah. So, but the idea is correct though. Like if you have a way of executing code that turns off this bit, so maybe you have a ROP chain that says, let me clear this bit in this page table. Then yeah, you could potentially then inject code and then execute it. That's correct. Okay, so this prevents so if you apply this no execute setting to the stack, this prevents you from both injecting code and then executing code on the stack is the idea. Okay, so the overflow, so it's important to note, the overflow can still happen. You can still inject the NOP sled, your shell code, and then overwrite this instruction pointer. What happens is when you try to return from this function call to the shell code on the stack, this is where you get the seg fault, because then the permission bits on that page say, hey, you're not supposed to execute from this page, and then you'll terminate. Okay, so this is basically turned on most binaries now, hopefully. You have to work hard to turn this off now. So that's a countermeasure. Okay, so then the question is, does this prevent return-oriented programming? It does not. So we just talked about how you could use ROP to turn this off and then inject shellcode onto the stack. And this is when we're talking about chaining exploits together. This is basically what people are doing now. They're chaining a bunch of things together in order to get their exploit to work now. So it's making life difficult for exploit developers. Okay, so the idea is that this dep doesn't prevent the overflow, but it basically prevents you the return into the shell code. Okay, so the short of it is that your permissions on your page now determine what the memory controller will allow. And so in this case, if you have, this is your page table, and you have your code, your text section in hex 1000, you typically in this memory page have read, but not write, and then execute on all of your code pages. So you have read and execute, or you have read and write, and then no execute are the typical settings that you would have. And so you can look at this, like when you do a cat /proc PID, and then the memory map of a process. These are all the virtual memory addresses that have been allocated to this process. And you can see for most of them, it's either read or execute. But if you had a read-write segment, then you don't have the execute. And if you go all the way down to the stack, you see that this is read and write, but it's no execute. So it's basically preventing you from executing code on the stack. Okay. Are there questions about no execute? This is just low-level operating system stuff. The next thing, which was referred to in the break, was some kind of polymorphism. And this is what address space layout randomization is. So the observation on stack smashing and any of these return-oriented programming exploits is that you need knowledge of the victim's memory layout in order to get the addresses onto the stack that you need to do your exploit. So what happens if the victim, whenever it runs its program, randomizes its memory space, randomizes where it places all of its essential data, all of its essential code, then you really mess up an adversary. Now the adversary is going to have to do more of a brute force sort of process to exploit your randomized process. Okay, there are some exploits that only need a relative layout, but most of the exploits out there do need to figure out actual addresses of the stack and the heap in order to actually work. So ASLR says randomize not only the location, but the size allocations of the data that you're using. Because again, we're trying to use the predictability of the memory layout to corrupt it in a way to get ourselves code execution as an adversary. So the victim randomizing all of that stuff, that throws a wrench into our entire chain. The nice thing about this is that this can all be done in the program loader, assuming you have relocatable code. Well, not the size allocation, but definitely the location, the location randomization, that can be done by the loader. The offset of the different segments in memory can be also changed, but that's what we're talking about here. Okay, so this can be done transparently to the application itself if you have compiled the application to be relocatable. Okay, this is what it looks like. So you have the executable, And then within the code, within its, so the text section, the initialized data, you basically randomize, and rather than using a fixed base address A, and then for the mapped memory, dynamic memory sections, the heap, the libraries, and the stacks, and then the main stack, each one of these is typically loaded with fixed base addresses, A, B, and C. So the idea of address-based randomization is to change that at the load time, to generate a random number when you invoke the process, the binary, and then within the loader, you bring these up into different locations before you load the binary up. And then this makes it harder for the adversary to do these memory corruption exploits. Okay, examples or questions about this? No. The next interesting thing is what they call ASCII armor. And this is very similar to that Terminator guard approach. The idea is if you need, this is the preventing of the return to libc ones. The idea is that if there's a critical address that the adversary wants to return to, make sure it's located in the low parts of memory that have what's known as within the ASCII armor. And an ASCII armor address is an address that has a null byte in it, right? And so at the beginning of memory, all of those addresses have null bytes in it. The problem for the adversary is that you can't return to one of these things because it'll automatically terminate your overflow if there's a null byte in your payload, right? So if you're trying to return to that address, you can get one null in there, and then all of a sudden your exploit, your stir copy terminates. So that's ASCII armor. And so putting this system library call at the beginning that has a null terminator in its address prevents you from actually creating the stack frame to inject bin shell. Your copy is going to stop right here. And then you're not even going to be able to put the full address of system in this stack. So that's the idea. So if your address for system was 01 null null 01, then you could only get the first 01 in there, and as soon as you write your first null, the stir copy terminates. If you're trying to exploit a stir copy. So that's basically ASCII armor. Yeah, I should mention that the ASCII armor works for any memory vulnerability from unchecked stir copy is this particular countermeasure. And this got put into the Linux kernel, and there is a plugin that allows you to do this from 2.4. So it's in the early 2010s. You could do something that looks like this. Another interesting thing is the shadow stack. So the idea is that you keep a secondary stack with all of the return addresses in it. And then when you return using your runtime stack, you just do a comparison of the return addresses on the stack. And if they match, you're fine. If they don't match, someone has messed up your stack. So the separate copy is a thing. You could actually do this by software. So you could actually add the shadow stack. Now, this is some overhead, obviously, because there's some copying going on. But both compilers, GCC is GNU's compiler, and then the Clang is this LLVM compiler. So both compilers allow you to add the shadow stack. And this became so prevalent that Intel decided to bake this into hardware. And that's what this Intel's control enforcement technology does. It implements the shadow stack, so you're not paying for the copy of that stack. You're actually keeping that in. It's kind of like hyper-threading, where you're keeping, in hardware, you're keeping that duplicate state, that extra state in memory. Okay, so in the function prologue, you add code to update that second separate stack. And then in the function epilogue, you check to make sure that the return addresses in that second stack match the return addresses of your current stack. And then if they're not equal to each other, so if the buffer overflow has corrupted any of these three return addresses, then you basically generate this fault, and then you return. Countermeasure number 8 is this control flow integrity thing. And so the idea here, this is a compiler. Well, it's a combination of a compiler modification with a microarchitectural addition. And the microarchitectural addition is this new instruction called end-branch. And the idea is that the compiler is going to label all the legitimate locations for you to do a jump from or a jump into. So you're like, oh, I'm going to compile the code and I'm going to look at all the indirect branches and indirect jumps. And I'm going to label those destinations for the legitimate code with the NBR instruction. It's basically a no-op. Like you're going to hit this thing and it's going to be like, oh, you're tagged as legitimate. So if you're the destination of an indirect call or an indirect jump, I'm going to let you through because you have hit NBR. If you have an indirect call or an indirect jump instruction that goes to an instruction that is not NBR, that means you haven't been blessed to do that. Like the compiler didn't expect you to be able to reach that location from an indirect jump or an indirect call, and this is what will terminate the program. And so this makes it difficult for an adversary to do return-oriented programming. Because again, in order to do the ROP, you're returning to these gadgets. And if the original binary didn't want you to enter any of those gadgets, then the fact that you're doing the return into those and it's not labeled with NBR terminates your program. So that's the idea of this. So you can actually add this with compiler flags if you would like. So here's the picture of it. When you compile this program, when in main, because this is a function call, it's okay to call main and have this be the target of your call because the NBR instruction is right at the beginning. If I compile as part of this compilation, I call F. I call foo. So foo is a function, and I set this function pointer to it, and then I invoke it. Because this indirect call goes to compiled code that is also labeled NBR, because this is a legitimate function call, then this also checks. But if someone corrupts this function pointer F to make it point to some arbitrary location within foo, this is basically going to exit the program because this was not intended to be part of your control flow. So part of control flow integrity is mapping out all the function call chains in your program and making sure you adhere to it, that you can't return into arbitrary locations in your code space, only in precompiled cases, locations that have this NBR end branch instruction in it. And again, this end branch is basically a no-op, but it's just labeling that you can return into that particular location. Okay, you could do this in software, but this is also part of Intel's control enforcement technology stuff.
This seems pretty low overhead. It's such a small instruction.
Yeah. Okay. So you can see this indirect call. So when you compile this thing, because it's a function pointer, you're loading a pointer into a register, and then you're saying, just call into whatever's in that register. So you could, as an adversary, corrupt this and then go to any location in this program. But because you can only go to things that have the NBR labeled, this forces you to remain in the control flow of that program. So that's CFI. Okay. Number 9, memory tagging. This memory tagging extension for ARM. And so this was meant more as a heap vulnerability detection or a heap exploit detection mechanism than a Stack Overflow. But the idea here is that when you allocate memory, you basically color it. So it's a coloring problem where all the different memory locations are colored with a particular color. And when you have a pointer that points to a buffer that's been allocated a particular color, it also is colored with that value. And then when you have an access into memory using a pointer, you make sure that the colors match. And if they don't match, then you have a memory out of bounds error, or you have a use after free error or other kinds of memory corruption errors. And so in this case, if I have a pointer that was allocated and pointing to this memory location that was green, and it tries to, because of a buffer overrun, read memory above it, this causes a fault. If this particular pointer has a bug where it gets set to point to something in this yellow memory up here, this will also fault. So that's the idea of memory tagging. This really matters in heap allocation. So when you allocate dynamic memory, so here's an example where you say, I need a new character array. You color the pointer that's returned from this allocation with blue. And so this is the colored memory in blue. And then everything around it is a different color. And when you try to go out of bounds, you have a color mismatch. The blue doesn't match the yellow, so this basically causes a fault. And then when you deallocate this memory location, one of the things that you'll do on the deallocation, you will recolor the memory to some other color so that if you reuse this reference pointer, you'll see a color mismatch again. And this basically detects any use after free vulnerabilities on the heap. And this is largely what Chrome is dealing with, the web browser. Like a lot of those memory corruption exploits are like use after free heap vulnerabilities. And so because you deallocated this and it turned this memory green, if you have a stale handle, a stale address that's still pointing there, and you're trying to use this memory location after it's been deleted, this mismatch will be caught. Okay. Other questions about memory coloring? I have 5 minutes, so I think this is the last one I'm going to cover. So the last thing is pointer authentication codes. So this basically, Apple put this into their phones, and they basically ARM, because the Apple phone is using an ARM based processor, ARM rolled this in to their ARM version 8 and beyond. So this is like 2017. So one of the things that they noticed was you have a 64-bit address in ARM, but there's no system on the planet that can implement a 64-bit memory space, right? We don't have enough memory in the entire world to be addressable with 64 bits. And so often when you actually have your device, the number of address bits that are actually being used is some smaller subset, usually like 40 bits of memory. 40 memory bits are used, and then the rest are actually they're basically not used at all. They're unallocated. And you see a pointer in memory, but the low 40 bits are being used for the addressing, and then the rest aren't. So the idea was, hey, why don't I store some cryptographic hash, some cryptographic integrity check as part of the unused bits in all of my memory pointers. And then if I have a pointer sitting in memory that the adversary is trying to hijack, then the adversary isn't going to be able to rewrite this integrity check, and then I'll be able to detect when these pointers have been tampered with. So that's the idea. Establish an integrity check. This is almost like a message integrity check code that we were talking about in the crypto section. I'm going to take up the original pointer, some context for which it's being used in, and some secret key, and then generate this pointer authentication code, and I'm going to fill in the unused bits with this pack. And then when I actually want to use this pointer, I'm going to validate that this all checks out, that this thing hasn't been compromised. And I do this for every pointer operation underneath. So I'm going to add special CPU instructions to calculate the pack, and then special CPU instructions to check the pack after when I'm about to use it. So that's what they added in. So this is what it looks like. So I'm doing this generation to create the pack and inserting it in the pointer, and then I'm going to check the pointer to see whether or not this thing is valid or invalid based on this instruction. So there's this pack instruction, pack star instruction. So there's a family of instructions in ARM that generate the pack, and then there's a set of instructions in ARM that authenticate the integrity of the instruction. So those are the two sets. This is what it looks like. So let's say I want to protect the return addresses on the stack. So the way it works in ARM is that there's this link register LR, and you can store this return address onto the stack using this instruction, store LR. Now, before you store this link register, I want to call this pack instruction to generate the pack code for this link register. And then that's what I'm going to store onto the stack. And if someone overwrites this return address on the stack, when I load this link register back from memory, I can call this authenticate instruction to check this pack to see if it survived. This is like sticking a canary inside of the unused bits of that pointer, is effectively what this thing is. Okay, and I go through all of this because this is one of the most hilarious vulnerabilities. The name. This is like the Pac-Man attack. So the Pac-Man attack is that if you can figure out this key, you see this key over here? If the adversary can figure out what this key is, he or she can infer the context and then figure out the pointer to generate the pack. And that's what the Pac-Man attack is to try and use speculative execution to reveal the key in pack so that you can basically do the memory corruption and recreate the pack so that the authenticate thing succeeds. So that's the full rabbit hole on memory corruption. And so we needed all of that. That's hundreds of millions of dollars, billions of dollars in damage, hundreds of millions of dollars of development just to fix this one problem. And so that was why I wanted to talk about your best bet to prevent all of this is to use something other than C and C++. And so I'll end there.